Hello, can you hear me?
Okay, please.
Okay, thank you for the introduction. I'm Patrick Blown. Thank you for your attention. And I'm from Finisar, Australia. And my presentation will be on optical bandwidth enhancement modeling for cascaded WSS, cascaded wavelength selective switches. So to give you an idea about what our work was about, what I'm showing here is a measurement of 48 WSS channels in a WDM system with a bandwidth of 50 gigahertz. So what this measurement shows up here on the top, it's essentially an insertion loss measurement. And the way it's calculated, or the way it's measured, pardon, is with a tunable laser. The tunable laser passes through the WSS and it sweeps across the full spectrum. And then there's a power meter. And then by looking at the transmitted power, you're able to take a measurement of the transmitted power and the insertion loss. So I'm just zooming in on a shape, on a particular channel shape here. This shape, this sort of characteristic channel shape, is quite important because it tells us lots of information about how the signal will perform with this channel. For example, we can calculate what its 3 dB bandwidth is. We can get an understanding of what its crosstalk is between channels. We can calculate how flat the channel is. And also, more importantly, we can build up an understanding of how this channel performs when signal travels through multiple WSS devices. And this is called cascaded WSS. What happens with WS cascades is that you actually get a reduction in the effective bandwidth. So for example, if we have a certain insertion loss on the edge, after passing through more and more WSS devices, you get a scaling. So the amount of loss scales in dB with the number of cascades. So this is actually a huge issue and a huge concern because some networks can have upwards of up to 20 cascades in WSS. And I'm sure you'll know that a reduction in bandwidth has a substantial impact on the network performance. And this effect is particularly of concern for the more modern modulation schemes, where there's much more emphasis on the edges of the channel. And we can see here in the figure how the 3 dB bandwidth evolves after cascades for this particular channel shape. So what do we do about this? How do we counteract this bandwidth narrowing? And the idea is that there are two main techniques. We can use what's called the electrical compensation method, where we apply DSP algorithms and FIR filters in the electrical domain at the transmitter and at the receiver. Another complementary way of counteracting this bandwidth narrowing is optically. We can do optical spectral shaping at the WSS itself. And both techniques are quite effective at counteracting this bandwidth narrowing, but it's the optical compensation that our work was focused on. In particular, the technique which we call optical bandwidth enhancement. So what I'm showing here in the graph is a number of slices. You can see here in the blue squares. These correspond to the pixel columns in the LCOS that form the channel. And then this dashed blue line here is showing you the optical response of that channel. And down here, I'm just showing you a measurement I've taken of a device of a channel. Now, with optical bandwidth enhancement, what we do is we enhance the transmission at the edges of the channels. And when you do this, you can see there's actually quite a substantial change in the channel shape. We can see if we zoom in on the channel edge here, there is a sharpness. The channel is sharper. And that is what means that the bandwidth will not reduce so quickly with cascades. And this technique, there are some in exchange, we have to have a little bit of additional insertion loss, maybe 1 to 2 dB. And also there is the addition, more importantly, the addition of this sort of spectral artifact, this sort of like ear, you could call it, on either edge of the channel. So this technique is in common use amongst the WSS vendors. So, but this shape, if it's so important, what are the models? How do we model this shape? And what I'm showing here in black is a measurement of a WSS, the insertion loss spectral transmission shape there. And I'm also showing you two of the major models here. In red is the so-called super Gaussian formulation. And it does appear like a WSS channel shape. Unfortunately, if we zoom in, we can see in red, it doesn't do a very good job at capturing the channel shape. And indeed, if we look right out on the edges, indeed, it doesn't do a very good job. And you can only really capture this channel shape in only one region of the channel shape. About more than a decade ago, my colleague, Sibi Pulakasarel, worked on a model which was based on the physical mechanism inside the WSS. And that curve, this equation is shown in green here. And you'll notice that this does a far better job of capturing this WSS shape. And if we zoom in here on the channel edge, we can see that indeed it does a very good job, but it's not quite there. And indeed, the reason for that is because this measurement is of a channel that has this optical bandwidth enhancement enabled. And so this model here, if we zoom right in and have a look at the differences, we can see up to 0.1 dB difference here, mainly because of this artifact. Now, this might seem like a small number, but after 20 cascades, this error increases to 1 to 2 dB. So this is a big concern. And if we use this model to try and predict what the 3 dB bandwidth is after cascades, we see actually quite a big deviation between the model and what is predicted by the measurement. And likewise, if we want to ask, how large does this ear get after cascades? Well, the current model doesn't tell you anything about that. So of course, there is a need for a new model that will correctly describe this artifact, this shape. And that's what this work is about. So I'll just give you an overview very quickly of how the current model works. Basically, we start off with this rectangular shape here corresponding to the channel. Then we fold in the optical transfer function of WSS itself, which is a Gaussian shape. And then we do a convolution of those two functions to give the final channel shape. And here is the expression here. This new model works, it follows the same methodology, except what it does is introduce direct delta functions on the edges of the channel, and the size of which is controlled by a new parameter called alpha. And we do the same thing. We convolve with this Gaussian function to give a new channel shape. And this is the new expression here on the right. We can see that indeed it looks very similar to that. In fact, it is the same equation, except there is this addition of a new term here. So how well does it do? Well, here, what I'm showing you is the same measurement before, but in orange, I'm showing this new equation, and we can see that it does a far better job indeed at fitting the measurement. And if we do the same predictions with the 3 dB bandwidth with cascades, we see a very, very strong agreement with that of the measurement. Likewise, with the artifact size, we can see that this model does a far better job at predicting the artifact size after cascades. So to get an understanding of how this new model, the differences and the improvements with this model, how does this translate to optical experimentation? So what we did is we did an emulation of 1 in 10 cascaded WSS using a 200G 16 QAM optical network. So the way we did this is we have our transponder here, And we have an ASC source that we can use to introduce noise. And then we then receive the measurement again, and we can use this to do bit error calculations. So how do we emulate 10 cascades of WSS? This is actually quite a challenging problem, because one might expect that you would need up to 10 WSS devices to do this sort of emulation. But fortunately, it's possible to emulate a large number of cascades, up to 10, using a single instrument. This is a WaveShaper B series. And with the WaveShaper, you can program it to have a particular shape. In this case, we've used the model, used the current model and our new model to generate what the curve should be for 1 and 10 cascades. And then we've done an emulation of that with the WaveShaper. So the target curves here, I'm showing here, are the dashed lines for 1 and 10 cascades for both models. And then we have the solid line, which is the actual experimental measurement of the WSS shape from the WaveShaper. So this shows us that the WaveShaper is actually capable of doing this emulation. And we did a comparison of the bit error ratios here. And here, this is what we found. Essentially, with the current model, the curves predicted by the current model, we find that the 1 cascaded result and the 10 cascaded result were essentially unchanged. So there was no difference between 1 and 10 cascades, according to the model that we have right now. But with the new model, what we found is that when we compared the bit error ratios of the 1 and the 10 cascaded result, we actually saw a discrepancy, a difference, in fact, a reduction in performance. And you might ask, well, why is that? Where does this reduction in performance come from? And the reason is because this new model is capable of capturing this additional spectral artifact that pops up with this technique. And after 10 cascades, this artifact is at least 0.4 dB in size. So with these artifacts, this is actually going to be an impairment in the performance of the network. And this was absolutely not predicted at all when you use the current model that is in the literature and in industry right now. So this really shows you the subtleties involved here and the importance of having a really accurate model to describe the WSS channel shape. So to close here, I'll just summarize what we've done. We've come up with a new expression that describes more accurately the channel shape of WSS filters that use this technique called bandwidth enhancement. Remember, this technique is essentially in common use now amongst the WSSs, and it produces more accurate predictions, and it gives you better information about what happens after cascades. With this equation, you're able to do a better job at improving system performance for future systems as well. And in the future, our work will be focusing on the capturing the statistical nature of the various parameters in the WSS so that we can do accurate Monte Carlo experiments using this new formulation. Thank you very much for listening to my presentation. And
Okay, thank you, the talk. Thank you, the speaker. Any question? Any question?
Oh, yes, Professor Zhao, I can see a question in the chat box.
oh,
Yeah. Can you see it? How can we extract the?
can you extract it? Yes, indeed, you can. You can extract this parameter sigma in reality. For one stage WSS, you would need to do a curve fitting. Ideally, you do a curve fitting for a large number of, as many WSS as you can. And then you will be able to extract that parameter. That parameter sigma is describing how what is the resolution of the WSS, and it's more or less going to be the same for a single product WSS product line. Yes, I hope that answers your question.
Okay, thank you. I have a question.
Yep.
Is there any effect of the new model for the switching time?
Pardon, could you repeat that question?
Is there any effective of the new model for switching time? Switching.
Oh, sorry, I think your internet connection has just dropped out. Could you repeat that last sentence?
The switching time will.
Oh, switching time?
Yeah.
Oh, so this model, no, this model doesn't take into account switching time, but you could imagine that you could devise a model that does include that as well.
Okay. Okay, any question? Okay, if no question,